Swayam Prabha. Digital India. Educated India.
Welcome to the DTH sponsored course on micromachining. I am going to talk to you about wire electric discharge machining as well as wire electric discharge micromachining. Acknowledgement. Advanced Machining Science book published by CRC Press USA. Help of Dr. Swayam Sharma and Dr. Mahavir Singh from IIT Kanpur. Mahavir Singh and others have written a chapter on micro EDM, modeling and optimization. And Mahavir Singh et al., they have also written a chapter on thin wall micromachining of titanium, aluminum, vanadium using micro wire electrical discharge machining process. So I have taken some material from these references. Organization of the talk: Introduction to wire electric discharge machining, which includes wire electric discharge micromachining, elements of wire EDM system, and other things I will discuss as the lecture goes further. Introduction: wire electric discharge machining as well as wire electric discharge micromachining. Both macro and micro are discussed in this particular lecture. Whether it is macro or micro, it depends upon wire diameter and machining parameter that you have chosen, so that you will see over here. So at many places I have written just wire EDM. It does not simply mean macro wire EDM, it also includes wire ED, MM, which depends upon again wire diameter and machining parameters. Wire electric discharge machining. Working principle of wire EDM process is the same as that of EDM process, except that here wire is used as a tool, and tool is made as cathode in EDM as well as in ECM also. The machining parameters ranges are different from that used in the EDM process, because EDM process normally is used for macro, while here wire EDM or wire EDMM is used for micro. For micro wire EDM, wire diameter should be well below 1 millimeter. Why? We will discuss it later. Workpiece material should be electrically conductive, otherwise it cannot be machined by wire EDM or wire EDMM process. Tool diameter ranges from 50 to 300 micrometer or 0.05 to 0.3 millimeter. Then you have stratified wires. What is stratified wire? Why we recommend stratified wires? We will discuss it in detail. Dielectric normally preferred is deionized water, but there are many other dielectrics which are used in wire EDM also other than EDM. And then you have material removal mechanism that we will discuss in detail. Here, because of sparking, a lot of heat is generated on the workpiece surface and between the workpiece and the wire. As a result of that, melting and vaporization of workpiece surface and to some extent wire takes place. Constant inter-electrode gap is maintained with the help of computer controlled positioning system. This is a very important aspect, because if you are not maintaining a constant inter-electrode gap, then the surface roughness as well as tolerances may not be good as per your requirement. It can cut complicated contours. I will show you some examples. It is a very good process. CNC controlled wire EDMM and wire EDM are very good for producing complicated contours. High, and this is also very good for 3D cutting that we will see. High degree of accuracy and good surface finish can be obtained if you are optimizing the process parameter. Experimental setup for EDMM and wire EDMM process. This is basically for wire EDMM process. You can see different parts over here. This is the photographic view. Wire tensioner. Here wire is used and it has to be kept under proper tension. Otherwise, you are not going to get proper surface finish, surface tolerances, and also sparking will take place, may take place, which will damage both workpiece as well as wire. Wire cut processing envelope, here wire cutting is taking place. Dielectric supply nozzle is here that you can see. Then workpiece fixture is here, and here is the workpiece. As you can see, spark is shown over here. This is the machining tank. Power supply is there. Then you have power supply to the wire, that is the connection given over here. And this is the used wire collection wheel. And then wire guide roller is there. It is guiding the wire under in which direction and it should go and what inclination it should move. And then you have the mid roller. And then finally here you have the wire supply pool that is shown over here. This is the wire electric discharge micromachining attachment in the DT110 machine tool. This is the DT110 is the machine tool which is being supplied by the manufacturer. Here you can see nice pictures of kerf quality. Kerf quality is nothing but this is the kerf which is where the material has been removed, or this material has been removed by wire EDMM or wire EDM process, and so this portion which has been cut is known as kerf, and whatever portion is given up, removed out, that is known as kerf loss. And this is the scale of 100 micrometer, so you can see this is around 100 micrometer width of the kerf. This is another one, kerf loss, and you can see this is the enlarged view of this part that is shown over here, and this is the scale. So kerf quality representation using optical microscope images of microcillet. This is known as microcillet. Machined at 2880 microjoule discharge energy and 0.72 microjoule discharge energy at feed rate of 6 micrometer per second and wire speed of around 10%. In wire ED, sorry, this is something wrong over here. Wire speed should be in meter per second, but this is feed rate is more or less the same as the wire speed. So we will see, I will correct it later on. In wire EDMM process, high discharge energy levels are preferred for enhanced material removal rate and relatively rough profile of the cut. Rough, depending on the nature of the cut required, kerf width and quality of the kerf are controlled. Magnitude of the discharge energy can be obtained using two different types of power generators. You know, low magnitude of discharge energy or high magnitude of discharge energy is obtained depending upon what kind of power generators you are using. It can be transistor based power generator or RC circuit based power generator. So here wire speed is not 10%, it has to be corrected. I will see it later on. Wire EDMM process characteristics. Wire EDMM is widely used for processing challenging to machine materials, or which are very difficult to machine. Those materials can be machined by wire EDM and wire EDMM processes. namely titanium, nickel alloys, carbide, stainless steel, etc. Typical applications of wire EDMM include thin wafer machining for solar cell, machining of nickel alloys for turbine applications, machining of delicate parts, namely miniature gears, micro tools, etc. I will show you later on miniature gears which have been machined by wire EDMM process. With the advancements in wire EDMM machine tool, materials as thick as 300 mm are precisely sliced or cut with an straightness accuracy of about 7 to 8 micrometer. The wire EDM is probably the most resourceful and versatile variant of the EDM process. Theoretically, there is no mechanical contact of wire with the workpiece unless short circuit takes place because of so many other reasons. Some of them we will discuss. Machinability is independent of the workpiece's mechanical properties, because here there is no direct contact of the workpiece and the tool, that is the wire. Rather, it is the melting and vaporization. We will see the principle. So, hardness, yield stress, toughness, etc. These are the mechanical properties of the workpiece material. They do not affect the performance of wire EDMM process, and high relative accuracy is achieved as compared to other machining techniques. It works on the same principle as EDM process. Spark generation between the tool, that is the wire, and workpiece takes place. Generated heat results in melting and vaporization or partial evaporation of the electrodes material. That is, electrodes include anode as well as cathode, and anode is the workpiece and cathode is the tool, that is the wire. It utilizes wire with a diameter of 30 to 300 micrometer as a tool electrode, and that is made as cathode. Two electrodes normally have a narrow gap of 20 to 100 micrometer submerged in a suitable dielectric tank. One figure we have already seen, others we will see. Among different dielectric fluids, hydrocarbon based, water based, gases, etc. Deionized water possesses the characteristics of low viscosity and high heat absorbing capacity, which are helpful in the wire EDMM process to prevent thermal damage to thin wire and its resulting breakdown. This is very important because wire should not break down, otherwise it may damage to some extent the workpiece also, and it takes certain time for rebounding the wire on the pulleys. An ultra thin wire is traveling continuously to feed an untarnished wire may be utilized as a tool electrode. Dielectric in wire EDMM, high frequency and comparatively low energy sparks create a high temperature plasma channel that expands the discharge time and generates high temperature. That temperature may lie somewhere between 8000 degrees centigrade to 10,000 degrees centigrade, and these temperatures have been calculated theoretically using various numerical techniques also for a very short duration. Eventually, melting of the base material occurs and intense heat flux may even evaporate the base material or parent material and a part of the workpiece material, that is parent material. The choice of wire material depends on several factors that cover proper wire tensioning, speed, and reduced vibration of wire electrode, because tensioning is a very important factor in wire EDMM and wire EDM because it controls the quality of the machine surface as well as the tolerances obtained on the machine surface or machine component. Commonly used wire materials comprise tungsten, molybdenum, copper, brass, coated wire, and coated wire normally has stratified wire. I will show you. Electrical power to the electrodes can be supplied through either resistance capacitance based power generator or a transistor based power generator. Both these power supply systems have their own merits and demerits. Some of them we will see later on, and some of them I have already discussed in the chapter on EDMM, that is electric discharge micromachining. Both power generators have their distinct advantages and limitations pertaining to particular machining conditions and desirability. RC-based power generators find their unique capabilities in the electrical discharge micromachining and wire electrical discharge micromachining processes. The wire EDM process utilizes a wire electrode or diameter in the range of somewhere 100 to 300 micrometer as compared to an extremely small diameter tool as small as 20 to 30 micrometer in the wire electrical discharge micromachining processes. This is very important to note. However, this definition which is given here for macro wire EDMM and macro wire EDM and micro wire EDMM process, it does not match with the definition of micromachining. We have already seen the definition of micromachining. Different researchers have given their own different definitions, their own views, hence do not get confused. Differences between wire EDM and wire EDMM processes. Here I have given some references and these references are given at the end, you can see them. Wire diameter in wire EDM normally ranges between 100 to 300 micrometer is used, while in case of wire EDMM they recommend less than 50 micrometer. Power generated in wire EDM is transistor based, while in wire EDMM it is resistance capacitance based. In discharge energy and pulse duration, you require comparatively high discharge energy and longer duration of the pulse in wire EDM. Here it is significantly low discharge energy and smaller duration of pulse power. Wire feed is a high feed rate in wire EDM and low feed rate in wire EDMM. Wire circulated continuously in wire EDM, while wire travels but not reused in case of wire EDMM process, because there are higher probability of breakdown or breakage of the wire in case of wire EDMM as compared to wire EDM. But whether the wire is recirculated in wire EDM, that also depends upon the condition of the wire before reusing it. It is not as a compulsorily rule that you reuse wire in wire EDM. Many times or most of the time it is not recirculated. Wire material molybdenum, brass, tungsten, while in wire EDMM it is tungsten wire is preferred compared to other wires. Dielectric deionized water is preferred compared to hydrocarbon based dielectrics. Hydrocarbon dielectrics can be used in case of wire EDMM process. I personally have difference of opinion with reference to this table in view of the definition of micromachining, because I have told that wherever there is a material removal or the feature created by any process, and if it is smaller than 1 millimeter, then in my opinion it should be treated as micromachining, or I can say wire electric discharge micromachining, rather than wire EDM. That is what they have told, that even with the 100 to 300 micrometer wire they are using, and where the width, kerf width will be around 400 micrometer, and they are still not counting it as micromachining or wire electric discharge micromachining. But anyway, it depends upon the viewpoint of different researchers. Now here I told you earlier that we have the wire that is known as stratified wire, and it is used in wire EDM process. And you can see here this figure, this is the coated layer thickness, and this is the core wire here. This is the core wire, and this is the coated layer thickness. This is the thickness over here, and this is the core wire. So two things are there. One is this core, another is the coating. We will see what it is and what are the uses of this. Charmills Corporation, Switzerland, they used to make this stratified wire for the use in wire EDM and wire EDMM processes. You can see here, core is made of copper drawn wire, and this coating or outside layer is made of zinc alloy, which has comparatively low melting point, and material removal rate is higher than when using bare copper wire. When you are using this stratified wire, you can get rather higher material removal rate compared to the plain copper wire when you are using, or bare copper wire using. Because what happens, I will explain you little later. More expensive, stratified wire is more expensive. Diameter ranges 0.025 to 0.200 millimeter. Wire is not recycled. It wears out, becomes weaker at many locations, and it is therefore not recycled to avoid the breakdown of the system. Also comparatively cheap. Now, to avoid wire breakage in supplying higher discharge energy, a stratified wire is used. It consists of a core wire coated with material such that it can handle a higher thermal load without breakage. So this is the coating which I have already told you, and this is the base wire or core wire, and a typical stratified wire consists of copper core that is coated with zinc or its alloys, and as you can see, the outer layer material has lower melting evaporation temperature. That means here zinc layer has lower temperature or lower melting and evaporation temperature compared to the core wire that erodes due to heat input to the wire. So once sparking takes place, so this outer layer melts and evaporates, and the core layer or core of the wire remains intact. As a result of that, the wire does not break even at higher loads. The inner core wire remains protected or intact, therefore allows higher cutting rate, because it allows higher current, higher temperature to bear. That's why it allows higher cutting rate at higher discharge energy condition. So this is the basic principle of stratified wire, why it can give higher material removal rate. Melting point of zinc, that is the outer layer, is smaller than the melting point of the copper, brass or the core material over here. This is the principle based on which this stratified wire works. So zinc layer will melt first. It absorbs latent heat of melting and vaporization of zinc layer, and core temperature is smaller or much smaller than the melting point of the zinc. A stratified wire can carry more current, which leads to higher energy per spark, and if higher energy per spark is there, then you will get higher material removal rate, because higher energy per spark will create higher depth of the craters being formed. In other terms, you can say higher material removal rate. CNC micro wire EDM process. Taper cutting using wire EDM. Whenever you are using this wire EDM system, the cut that you are going to get, or the machine surface you are going to get, is not straight sided, rather it is tapered one. And this is the system. As you can see here, various parts are shown, which I have shown to you in the figure earlier also. You have the V drive, you have the U drive over there. This is the workpiece, this is the wire. You can see here taper angle is there, and this is the taper angle, and you can tilt the wire so that curved, tilted 3D surfaces can be machined. You have the work table over here, this is the workpiece, and lower wire guide, and this is a wire feed. After using the wire, it is fed, rolled over this, and x-axis is there, y-axis is there. You have the control unit over there, and this is the upper wire guide. Wire is coming from here, traveling like this with the help of the guide. Here it is cutting this workpiece material by sparking, and then coming out and rolled over this. And once it has completed, or a whole wire has come over here, it is taken out. Possible to achieve around 0.1 micron feed, 1 micrometer table positioning accuracy. It reduces corner error, suppress wire vibration, and reduced crack surfaces. Because vibration is less, then crack surfaces are minimized. Fine finishing, power supply, high quality surface finish is obtained when you are using fine finish, and this is normally less than or equal to 0.1 micron. Introduction to wire electric discharge micromachining. Main differences between wire EDM and wire EDMM. Difference in the size of the wire responsible for creating the kerf. I have already shown to you in the figure in the earlier slide what is the kerf. So difference in the size of the wire is responsible for creating the kerf. You can see another picture over here. Wire feed, this is the wire take up wheel moving like this. Wire guide is there, wire is here, wire feed direction, wire guide is there, it is coming over here, wire supply wheel is there, and this is the dielectric, this is the wire, this is the workpiece over there which will be cut by sparking, and this is the inter electrode gap, the gap between the wire outer surface and the surface which is to be machined on the workpiece. And this is the power supply. You can see wire is made as cathode by connecting it to the negative terminal, and workpiece is made anode by connecting it to the positive terminal. A schematic diagram of a typical wire EDMM system for slicing or machining operation. In wire EDMM, tool is a wire which can be connected to the negative terminal, you can see over here, of a pulsating DC power source. This is a pulsating DC power source, and this wire traces a defined trajectory in the workpiece. Dielectric fluid such as deionized water or kerosene oil is supplied between the two electrodes, and a feature of the desired shape and dimensions is created or is machined, and these are the two electrodes. This is the one, and this is the another. This is the cathode, this is the anode, and dielectric is being supplied over here. Main advantage: there is no physical contact between the tool and workpiece. You can see both are separated by a gap equal to inter-electrode gap. No mechanical residual stresses, because there is no physical contact, so no mechanical forces, hence no mechanical residual stresses are developed in the machine workpiece. However, thermal stresses are present as the material is removed by melting and vaporization, because this workpiece is subjected to very high temperature, and once material is removed, some heat remains over there and you get thermal residual stresses. Bowing of wire. Distance between wire and workpiece is approximately 25 microns in kerf, and gas bubbles rush to escape. So pressure on the wire, when gas bubbles are rushing to escape, then they apply the pressure on the wire. As a result of that pressure, wire bends, and this bending of the wire leads to inaccuracy, and different interelectrodes along its axis become, and sometimes it may touch even the workpiece, and if it touches the workpiece, short circuit takes place and wire gets broken. To minimize bowing of wire, increase the tension on the pulleys. To increase machining rate, multiple machining heads can be used rather than single machining head. Microwire EDM machine. CNC microwire EDM machine. You have the CNC computer numerical control of the wire EDM or microwire EDM machine. They are available in the market. Other measures to control bowing of the wire or appropriate machining conditions you should have. For this controlling the bowing of the wire, you should have appropriate machining conditions, specifically the frequency, current, etc. Elements of wire EDMM system. Now let us see the elements of wire EDMM system. Ultima model wire EDM of Electronica Pune. This machine is being manufactured and sold by Electronica company. You can see this is shown over here. This is the wire EDM machine. This is the control. This is the dielectric tank. Other control panel is here. Power supply is here. Its name is Ultima 25. You can see the internal view. Here is the wire, and this is passing through this. Here you will place the workpiece. Other arrangements are over here, and axis, XY axis movement, Z axis movements are controlled with the help of the motor. Wire electric discharge machining, power supply system. These are the elements: dielectric system, positioning system, and drive system. So these are the four main elements of the wire EDM and wire EDMM system. Power supply system, it supplies you or gives you pulse frequency as high as 1 megahertz or so, and reduced crater size or better surface finish is obtained. Larger the pulse frequency, smaller would be the energy supplied to the system or to the workpiece, and you will get the better surface finish. A smaller wire size is used. Current carrying capacity is normally less than 20 ampere. Wire EDM, traveling wire EDM system. You can see here something we have already seen over here. This is the wire take-up reel, wire guides. This is the numerically controlled XY axis. This is the workpiece. This is the dielectric is being supplied. Wire is there, and inside this is the kerf. That is the width between the machine surface, two surfaces. As you can see over here, this is the wire, this is the wire diameter, and this is the spark gap, and this is the kerf slot, and this is the wire supply view. This is another view for the same thing, consisting dielectric, wire guides, etc. Power supply is there, workpiece is here, and these are the kind of the slots that are machined on the workpiece by wire EDM or wire EDMM system. Power supply is pulsating DC. Then you have compared with band saw. You can compare it with band saw. Material removal rate and quality is the function of wire diameter and machining parameters. Sparking takes place between the wire and the workpiece. This is the wire and this is the workpiece. Sparking takes place between the two because dielectric is being supplied and wire acts as the cathode, workpiece acts as the anode. It erodes both wire as well as workpiece. Now this is to be noted that as sparking is taking place, a small part of material is removed from the wire and a comparatively larger part of material is removed from the workpiece. So both are eroding at the same time. Dielectric normally used is deionized water as dielectric. Other dielectrics also are being used, but this deionized water has its own merits. Some demerits are also there. Its low cost, low viscosity, efficient flow of water is there compared to other dielectrics. No fire hazard in case of deionized water, and you have high cooling rate and high material removal rate and high tool wear rate. This is the disadvantage, that when you are using deionized water, tool wear rate is also high, which we do not really want. It does not affect performance. Reused after filtration. Dielectric is reused after filtration or proper treatment. It is quite expensive. 5 micrometer size disposable filters are used for filtration of the dielectric. Additives are added to minimize rusting of the parts in which contact the dielectric comes. Positioning system. CNC 2-axis table is there which controls X and Y movement of the workpiece. Adaptive controlled mode is there. In case of short circuiting, because adaptive control is there, so in case of short circuiting, inter-electrode gap too small or wire workpiece too close, then they touch each other and short circuit takes place. At that point of time, this AC, adaptive control, moves back to re-establish proper cutting gap condition. That means it moves the workpiece back so that the proper inter-electrode gap is maintained and short circuiting is many times avoided. Wire drive system functions. It delivers fresh wire continuously and keeps wire always under tension. This is very much needed. I have already mentioned to you that if it is not in proper tension, then loose wire may touch the workpiece, short circuit may take place, wire may break and workpiece may also get damaged. For high quality, avoid taper, streaks, etc. So for avoiding taper, you have to design the tool, you have to design the machining conditions properly so that you get minimum taper on the machine surface. It minimizes wire breakage frequency. Wire guided by wire guides. You can have the sapphire guides made of sapphire material, or you can make these wire guides by diamond also. They are quite expensive. Wire movement towards take-up spool. Series of tensioning rollers are there, and tensioning of the wire plays very important role. Automatic reloading of broken wire. To enhance productivity, there are the devices which automatically reload the broken wire onto the pulley. And then to run the machine unattended, because many times in many countries people start the machine in the evening hours, they go home and they automatically keep running. If by chance wire breaks, then they have automatic reloading of the broken wire, and the performance of the machine is affected, but it keeps on working continuously 24 hours, even without attendance of the operator. Wire material, we have already seen, small diameter wires are there, maybe as low as 0.15 millimeter or even few tenths of micrometer diameter of the wire may be there for electric discharge, wire electric discharge micromachining. Large diameter can be as high as 0.15 to 0.3 millimeter, that is 150 to 300 microns. Copper or brass wires can be there. Wire discarded after used once. This is very important point, because after wear at leading surfaces, it no longer remains straight, it is no longer strong enough, and when if you are reusing it, it may break quite frequently. Hence, it is not recommended to reuse or to recycle the used wire. Process variables, we have seen linear cutting rate depends on thickness of workpiece, but not the complexity of the cut. Highest wire speed is normally 40 millimeter per second. Hybridization of wire EDMM process, important. Hybridization of wire EDMM process, wire electric discharge grinding. You can see here, this is the workpiece, and this is the wire cathode, this is the anode, and you have this wire moving there. Sparking takes place between the two, and you have the grinding kind of operation on the workpiece. Simulation image showing electrolyte velocity vectors in case of rotating helical tool. This is helical tool over there. Ultrasonic vibration assisted wire EDMM process. Now here you are giving ultrasonic vibration to the wire or to the workpiece, and you can enhance the performance of the process. As you can see over here, transducer and all other things are shown over there. A schematic diagram of ultrasonic aided wire EDMM setup. This is the workpiece, this is the wire. Sparking will take place between the two, and you will have the power supply. Then you have the ultrasonic generator is there, which can vibrate the wire at ultrasonic frequency. You have the transducer. This is the bottom guide and wire holder. Process parameters and characteristics. These are the different process parameters of wire EDMM process. Input process parameters, electrical parameters are here: resistance, threshold value, capacitance, open circuit voltage. In case of wire based circuit, we have already seen these two: wire RC based circuit and transistor based circuit. And in case of transistor based circuit, you have current, duty ratio, gap voltage, and pulse on, pulse off time. These are the parameters of transistor based circuit. Then you have non-electrical parameters like wire diameter, wire material, wire tension, wire traveling speed. All of them are going to affect the performance of the process. And then you have dielectric, which dielectric you are using, what is the viscosity, what is the conductivity, and so on. Interelectrode gap, feed rate, dielectric pressure. These are the miscellaneous parameters. Now there are certain responses with the help of which you can evaluate the process performance, and those responses can be material removal rate, kerf loss, we have already seen kerf loss, corner radius, wire breakage, surface roughness, the machine surface roughness, height affected zone, recast layer thickness. These are some of the responses with the help of which you can evolve or evaluate the performance of the wire EDMM and wire EDM process. This is known as fishbone diagram. Process characteristics. what surface you are going to get by wire EDM and wire EDM is known as met surface. Craters are formed. Craters help in retaining lubricating oil. If the component is having the friction, then you are going to oil it, and that oil can be retained by the crater formed by wire EDM or wire EDM process. Increased die life. Then you have surface roughness in finish pass, which can be around 0.1 micrometer, but all this depends upon the machining parameters that you are choosing and the workpiece material. Tolerances you can get as good as plus minus 7 micron. Applications you have many like dies, press tools, electrodes, etc. Effects of capacitance on machining parameters. Higher or lower energy per pulse can be achieved by suitable selection of capacitance. Energy per pulse E is defined, is represented by the letter E, and it is given by E is equal to half CV square, where C and V represent capacitance and voltage respectively. So you can calculate the value of E if you know the value of C and V. For wire EDMM, reducing the capacitance C will substantially reduce the energy per pulse. The obtained single crater size depends on the energy per pulse, that is E, which determines the minimum feature dimensions that can be accomplished, and it also affects definitely the final surface roughness that you are going to achieve. The pulse on time, that is discharging time, pulse off time, that is the charging time, and machining current are direct functions of capacitance. The higher the capacitance value, the higher is the charging and discharging time, and greater will be machining current. So higher, if machining current is higher, then definitely you are going to get a higher material removal rate. But I have already told you in other lecture that higher the material removal rate, lower will be the surface finish. That means higher RA value will be achieved. Parametric analysis, let us see material removal rate, and this is the current, and we know higher the current, higher will be the material removal rate, and higher the current, higher will be the crater size, hence higher will be the RA value, that is the surface roughness value. Here pulse on time, as pulse on time is increasing, energy per pulse is increasing, and if energy per pulse is increasing, material removal rate will increase and RA value will also increase. But an optimum is seen over here, beyond which both of them start decreasing. Then here wire speed, as wire speed is increasing, material removal rate and RA value both will keep increasing. But after an optima, as you can see over here, they start decreasing. And same is true with wire tension. Up to certain wire tension, material removal rate and RA value are increasing, but then they start decreasing beyond this optimum value. Process parameters and responses in wire EDM process. This we have seen. This is the kerf that is being created. This is the wire. Now important point to note here is, you can see the kerf width is always larger than the diameter of the wire, whatsoever may be the difference. But this is bound to happen so that between the wire and this surface being machined or machined, dielectric can flow, sparking can take place. So you can see here, this is the A, that is the inter-electrode gap, you can say in some sense, at this point, that is the gap between the wire surface and the surface being machined, and this is known as kerf width. So kerf width is equal to wire diameter plus 2 times lateral discharge gap A, that is this particular. So YK is equal to D plus 2A. You can see other picture where this kerf is shown over here, and it is quite rough. Kerf sizes are quite rough, 30.8 micron, and wire diameter is 30 microns. So you can see the kerf width is also always larger than the diameter of the wire, and this is natural. Components made by wire EDM, you can see over here. These are some of the components that have been made by a wire EDM process, that is stator core, stamping die machined by wire EDM. They can be made by other processes also, not necessarily on wire EDM, but wire EDM process can also be used for that purpose. Wire EDM taper cutting mechanism. This is very important component. 3D component has been made that is tapered in nature, you can see, and 3-dimensional, and it has been cut with the help of wire EDM. Example of complex shapes that can be cut by wire EDM and taper cutting mechanism. Potential applications you can see over here. Machining of fir tree slots in turbine disc tenons. Over here you can see that is shown over here. Then you can see micro gear machining. These are the micro gears, and these are the shapes that have been machined over here. And these are all in terms of microns. Then compound tool fabrication of EDM. You can see multiple tools that have been fabricated by wire EDM process. You can another view. Then thin wall micro machining for slicing of wafers. This is the slicing kerf. This is the thin walls over there. You can see the enlarged. This is the curved one that has been achieved over here, and deflection of wall thickness less than 10 micron. This thickness that has been achieved is less than 10 micron. Now fabrication of compliant mechanisms that you can see over here, they have been fabricated by wire EDM process. Low electrode wear EDM, 0.1% tool wear during machining. You can see here. Use of controlled wave form machining. Controlled wave form, you can use different wave forms for controlling the machining characteristics to reduce the wear of the tool, especially wire EDM with orbital motion, NC wire EDM, and die sinking EDM. Machining accuracy is 1 to 2 micron, and material removal rate may be as good as 5 millimeter square per second. Use of APT, automatic programming tool, for part programming is very important. English like language can be used in APT, like L1 is equal to line, point B1 P2, go to point 37, etc. And this is very simple, but this is very useful for NC part programming, where you are using APT language. And once you have the good part program, you can get good quality products machined by this process. Technological innovation in EDM further. Automatic wire feeder, we have already discussed it. EDM with adaptive control, optimum machining conditions can be maintained during machining. Objective, higher productivity and better quality. Controllable variables, that is the current, pulse duration, off time, feed rate, on time, and so on. Fuzzy adaptive control system, I am not going to discuss, but the fuzzy adaptive control systems are available. Machining rate is proper or not. It can be recognized from fuzzy rules. Describing experimental knowledge. Action phase, optimum machining condition. This is just to machine or wire EDMM all the time under optimum condition. This type of a controller helps a lot. Conclusions. This presentation can be concluded by the following noteworthy points. Wire EDMM process is an adaptation of the traditionally used EDM process. It is widely used for the processing of challenging to machine material, means materials which are hard to machine or difficult to machine. Those materials can be machined, shaped by this particular process. namely titanium, nickel alloys, carbide, stainless steel, super alloys, etc. Typical applications of wire EDMM and EDM include thin wafer machining for solar cells, machining of nickel alloy for turbine applications, machining of delicate parts, namely miniature gears, we have already seen miniature gears, micro tools, etc. To avoid wire breakage and supplying higher discharge energy, a stratified wire is used. How it works we have already seen, stratified wires and what are its advantages. It consists of a core wire coated with a material such that it can handle a higher thermal load without much breakage, and we have seen that this coating was one of the material used for coating was or is zinc. Higher machining current refers to more significant ionization in the gap, resulting in higher heat flux being applied to the or being supplied to the workpiece. Larger and deeper craters are obtained, therefore both MRR increases and surface roughness value also increases. It is possible to combine wire EDMM with other techniques for developing hybrids of the process or hybridization of the machining process. The hybrid process combines the advantages of the individual processes. These are the references which I have quoted there. Thank you very much.